Simple harmonic motion is that motion in which an object moves back and forth over a fixed path, returning to each position, velocity, and acceleration after a definite interval of time. Does that clear it up? Well, basically it's just something going back and forth, and it just repeats that pattern. So after a definite period of time, it will go back to the same position it had, the same velocity, and the same acceleration. An example would be just simply a pendulum going back and forth like that. After a definite period of time, everything repeats and it does it all over. You could have a cart moving back and forth between two springs on a track like this, and simple harmonic motion. Or you could have a mass bobbing up and down on a spring, and it's just repeating itself over and over and over, returning to the same position, the same velocity, and the same acceleration after a definite interval of time. All right, so physics. What do you think we're going to do with this? Well, we'd like to be able to predict. We'd like to, and that's all about physics, is making predictions. We would like to be able to predict what the position is going to be, what the velocity is, and what the acceleration is at any period of time. So we're going to find each of these as a function of time. So I know where it is right now. Where is it going to be 100 seconds from now? Okay, so once we get a handle on simple harmonic motion, we can extend that to a variety of things. One thing would just be like a pendulum clock, a grandfather clock. It just swings back and forth, and knowing about how that works will allow you to keep good time. Or if this car hits a pothole and that tire bounces, that spring is going to oscillate at a particular rate, and knowing about simple harmonic motion can predict that rate. And then once we know about springs bobbing up and down and pendulums swinging back and forth, things like that, we can use those ideas and build on those ideas for anything that is just simply going through a repetitive pattern. A sewing machine, just the needle just goes up and down, but all these internal parts are going back and forth, and they're at different positions and velocities and accelerations at different times. And that's how you coordinate all those gears and levers and pulleys and things like that inside a sewing machine. Even an engine with the rocker arms and push rods and valves, all of those is a beautiful course of things moving together and knowing where they're going to be at the right time. Later in the semester, we're going to look at waves and sound, and transverse waves and longitudinal waves. This would be like a string bouncing up and down, or air moving back and forth. It just moves back and forth in a very repetitive pattern called simple harmonic motion. So we're going to start out with this first case here with this mass bobbing up and down on a spring. And one thing I want you to notice here is how blurred the picture is here, because the mass was moving very fast right through that equilibrium position. If we let this just dampen down, like slow down over time, it's going to come to a rest right here. But that when we raise it up to here and let go of it, or pull it down to here and let go of it, it's going to be going the maximum velocity right through there. And we'll talk about why that's the case. But that position is called the equilibrium position. If you pull it above that to its maximum position, it's called its positive amplitude. And drop it down to its lowest would be its negative amplitude. And so we have a meter stick here, or in centimeters here, but it looks like equilibrium position is at 25 centimeters, and we raised it up to 30 centimeters and 35 centimeters and dropped it down to 15 centimeters. Even though you subtract 35 from 15 and get 20, the amplitude is just 10. The amplitude is the distance from equilibrium position up to its maximum positive or down to its maximum negative position. Okay, and then we remember about Hooke's law, where the further you stretch the spring, the more force there is. So the spring is not very stretched right now, so it's not going to have very much force from the spring. Here it's more stretched, and here it's even more stretched, so more force. And we remember from Hooke's law that it is a linear relationship. Now the mass of that doesn't change, so the weight of that thing doesn't change. And we remember that mass times gravity is weight. So that would be the weight of it here, same weight there. But if we look at the combination of those two forces, or the net force, there's a net force in the down direction here. No net force here, because the spring is pulling up just as hard as gravity is pulling down. And then there's a net force there. One thing to realize is that this mass is accelerating from here all the way through here. There's a moment when it's not accelerating because there's no net force. But that acceleration is not uniform. It's not keeping the same acceleration all the way through like it would if you just dropped that mass in a gravitational field. And the reason is, the further you stretch the spring, the more force the spring provides, and more force is more acceleration. Let's look at it in this case. So this would be the equilibrium position of the cart. This is where it's going to finally come to a rest if friction is slowing it down. And maybe I should say also that right now we're not really looking at the case where friction slows it down. We're saying this is simple harmonic motion versus dampened or a more complex harmonic motion. So we're pretending that this just goes back and forth and repeating the exact same pattern every time. We had to stretch these springs to get them attached here and stretch the spring to get it here. So at equilibrium, there's already a force from each of these springs, but that force is equal, so there's no net force. And what we want to do is see how the two springs play together to produce a predictable amount of force. So we moved this cart from the equilibrium position out to a new position, and we displaced it by this amount. So that original force is going to have added on to it the extra amount of force. We recognize that piece as Hooke's law. And then this spring wasn't as stretched as far, so the original force is going to be dropped or lessened by the same factor. So the net force in this position is just going to be that force of the longer stretched spring minus the force of the shorter, now less stretched spring. So we're going to subtract those two. We're going to distribute the negative. That negative is going to go here and here. So that term becomes positive. This term becomes negative. Here I have a positive force of the spring and a negative force of the spring. They cancel out. But here I have kx and another kx. So I get 2 kx altogether. And what that means is, if this spring has a spring constant of k, and this spring has a spring constant also of k, the combined spring constant would just be 2k. And that may have been a little hard to see because one spring was getting stretched more and the other was getting stretched less, but how they play together is just going to be Hooke's law, but at twice the spring constant. So in order to predict where this is going to be at a function of time, let's first do it as a function of its position, where it's at. So we're going to pull it all the way back here to positive amplitude, and so which would be 50 centimeters here. This was the equilibrium position, and then it would go all the way here to negative 50. But we'd like to predict how fast it's going when it gets back to right here. So we started from rest, and the spring was stretched the most, so it has the maximum acceleration, and that negative just means its acceleration is to the left. So right out here at its amplitude, it has the most acceleration, and that's because the force is the greatest due to Hooke's law. And then when it gets over to here, now the spring is stretched most here, it has maximum amplitude there. When it gets to the middle, those two springs provide the same amount of force, so no net force. And right there in the middle, it won't be accelerating, but it did accelerate from here all the way up to here. and then it's going to slow down all the way to here. From here, it's going to be accelerating all the way till it gets right here. So because it was accelerating all the way up until it gets here, that's when it has the maximum velocity. It's going to be going the fastest. Somewhere in the middle, it's going to have a velocity somewhere between 0 is what it would have had here, and its maximum, which would have been over here. But the acceleration is going to be just half as much. And the reason is the displacement from here is half what it was out here, and half the displacement would be half the force, and half the force applied to the same amount of mass would be half the acceleration. So let's go ahead and predict what would be the acceleration when it gets right here. In fact, we're going to let go of it and watch it go there, and it's going to stop right there. The velocity was to the right, but the acceleration was to the left. And that's because that spring was pulling harder, and there was a net force to the left. It was slowing down. Okay, so let's go ahead and calculate what the acceleration is. How are we going to do that? Well, we're going to do it the way we always have done that, with Newton's second law. If we know how much force is on that mass and how much mass it has, well, then we can calculate the acceleration. And we use Hooke's law to calculate the force, kx squared. This is the spring constant, and it's I said x squared. The spring constant times x, just its displacement, would predict the force of the spring. And that is going to be the net force on that mass. So we can combine those two. This is how we calculate the force on the mass divided by the mass would produce its acceleration. So we do need to know the spring constant, and we do need to know the mass. And I can predict what the acceleration is at any position. We were wanting to find its acceleration at a position of plus 0.25. So it looks like the acceleration is going to be off to the left, and I had to throw in a negative there, okay, to realize that the acceleration was off to the left at 1 meter per second squared. So it was fairly easy to calculate the acceleration of the thing. It's just Newton's second law. But now I want to figure out how fast it's traveling when it gets back to that same point. So how fast is it traveling? Right there. And at that moment, it was heading to the right, so its velocity is to the right. So we want to calculate how fast it's going. Conservation of energy is going to be the key. Well, what kind of energies are involved? Well, those springs are stretched, so those springs have potential energy. We recognize the potential energy of a spring as 1/2 the spring constant times its displacement squared. Okay, that's the potential energy of a spring. What other kind of energy is there? Well, there's kinetic energy. Okay, so this equation says we need to know the spring constant. This equation says we need to know the mass. And we're going to combine those two things to figure out how fast it's going. Well, right here, the spring is stretched, so it has some spring potential, and the cart is moving, so it has some kinetic energy. So we're going to just take how much energy the spring has and add it to how much kinetic energy the cart has, add those two things together, and that's going to be the total energy of the system. Well, if I knew the total energy of the system, then I could calculate how fast it's going. Well, what's going to be the total energy of the system? Well, by the time that cart gets all the way back to its amplitude, it's going to have no kinetic energy. That term is going to be 0. But all of the energy will be in the spring. So it's 1/2 kx squared, but our x position is all the way out at its amplitude. Okay, so when the cart gets to its full amplitude, it has no kinetic energy. All the energy is in the spring. Okay, that's our equation. So there's a 1/2 in every term, and I can cancel the 1/2 out. I plug in the variables, the position when it was stretched. We don't know its velocity, but that's the only thing we don't know. So then we just solve for velocity. I got to take this term and move it over to this side. to get this term by itself, and then I'm going to divide both sides by 1.5, and then take the square root to get velocity by itself. You do all that, and it looks like the cart is going to be going 0.88 meters per second. All right, let's just do some vocabulary now, introducing the idea and the difference between period and frequency. I'm using a capital T here because capital T stands for the period, which is the time it takes to make one complete oscillation or one complete cycle. Frequency is just the reciprocal of that. Frequency is how many cycles it makes in 1 second. So if we start our timer here, 1, 2, 3, 4, 5, 6, and it looked like that was going 2 times every second. So in 6 seconds, it made 12 cycles. So you divide those two out and find that the period was just half of a second. It took half of a second to make 1 cycle. And then the frequency is the reciprocal of that. It did 12 cycles in 6 seconds. So that's 2 cycles per second. And we call that Hertz, abbreviated Hz. So 2 cycles per second is what that was. Let's do this here. We're going to let this go for 1 second. So 1, 2, 3, 4, 5, 6, 7, 8. You can count fast. In 1 second, it made 8 cycles. So its period was 0.125, but I rounded up to 1.3 because we only had 2 sig figs. And then frequency, it made 8 cycles in 1 second, so its frequency was 8 Hertz. We'll do that one more time. This time we're going to let this just make 1 cycle, and we count 1, 2, 3, in 4 seconds. That made just 1 cycle. So 4 seconds for 1 cycle. The period was 4 seconds. In 1 cycle, it took 4 seconds, so its frequency is 0.25 Hertz. Period and frequency are reciprocals of each other. So just a brief reminder about angles in radians. 1 radian is the angle where the length of the arc equals the length of the radius. So how many radians are all the way around? Well, that's 1. That's 2, 3, 4, 5, 6, and a little bit more. If we wouldn't figure out it exactly, we would figure out how many radii fit into the entire circumference. So how many radii fit into the entire circumference? And the circumference is 2 pi r. And how many radii fit into that? Well, it looks like just 2 pi. 1 rotation is 2 pi radians. And the neat thing about doing it in radians is if we take the length of the arc, we measure it in meters, the length of the radius we also measure in meters, it cancels out so that the angle isn't really a unit. We call it 1 radian, but radians is a unitless unit. The advantage to that is if this is measured in meters, we multiply by a thing that doesn't have any units, we could get a distance measured in meters. Or if we take an angular velocity in radians per second, multiply by meters, we get meters per second, a tangential velocity. Or if we take an angular acceleration, radians per second, multiplied by meters, we're going to get a tangential acceleration of meters per second. And all of this was a review of what we did in circular motion. So an angular velocity is a number of angles divided by the time that it took to go through those angles. And then this was a lowercase t because uppercase T is specifically the time to make one complete oscillation or cycle. So going all the way around, the angular distance all the way around divided by the time all the way around would be the angular velocity. And if we just kind of hide out that and just look at this for a second, rearrange that and solve for t, we get that the period is 2 pi over angular velocity. And don't forget that the period was also the reciprocal of the frequency. Okay, so that's an equation that's on our equation sheet, and hopefully we now have some sense of the meaning of that equation. If we just look at this piece right here and cross multiply, the angular velocity is going to equal 2 times pi times the frequency. So angular velocity is 2 times pi times the frequency. Okay, we'll want to tuck that one away as well. If I look at this piece of it here, we can see that we can find the angle by taking the angular velocity times time. So the angle is angular velocity times time, or 2 pi f times the time. Okay, so we're getting to have a few more variables we got to keep track of here. But the angle that we've moved through is 2 pi times the frequency times the time. We can make sense of that because 2 pi is how many radians are in a complete cycle. Frequency is how many cycles go by every second. And time is just measured in seconds. So cycles cancel, seconds cancel, and when we do that, we're just left with an angle in radians. All right, so let's practice that. Let's say that this thing is rotating at some velocity, angular velocity, but the period of it is 4 seconds. It takes 4 seconds to go all the way around. So 2, 3, 4 seconds to go all the way around. If that's its period, well, its frequency is going to be the reciprocal of that. Now this thing's going to be going the same angular velocity, but we want to figure out at what angle will it be after 2.8 seconds. Okay, so we just take 2 times pi times the frequency times the time, and we find that it's going to be rotated through 4.4 radians. Now remember this piece here, this was radians per cycle. If I had done that as degrees per cycle, that'd be 360 degrees in a cycle, and times cycles per second times seconds, we would have found that it would have gone 252 degrees in 2.8 seconds. So in 2.8 seconds, right there, that was 2.8 seconds, and that's 250, just a little bit more. Just a reminder about this equation here is that it only works if we measure the angle in radians. It wouldn't work if we measure the angle in degrees. So why are we talking about circular motion? Well, here's the beauty of simple harmonic motion. This is going to be, when this is moving in simple harmonic motion, circular motion can be used to describe its motion. See how this mass is staying horizontally in line with that ball moving in a circle here. So as that ball moves in a circle, it has the exact same up and down motion as this up and down motion. And we're going to use that fact to find position as a function of time. So it also works on here. So what we're going to do is we're going to let this go back and forth, and we can see as it goes back and forth, it stays vertically in line with that object. I do have my circle shrinking here because it is losing energy. The amplitude is changing. But the radius of this circle is the amplitude of where that cart is at its maximum displacement. So what we want to do is relate that to angular velocity. So this is going through a certain number of angles every second, and it has a particular angular velocity. Okay, and we can figure out what angle this ball is going to be at by 2 pi times the frequency times time. Well, we can predict what the angle is going to be, but we want to predict what its position is going to be. Well, its position is just going to be the amplitude times the cosine of that angle. Okay, hypotenuse times the cosine of that angle is its position. So the amplitude times the cosine of the angle will tell you the position. We have just found its position as a function of time. So we're going to tuck that one up here because we're going to keep track of these as we go. We've just found position as a function of time. And a pendulum works the same way. This is a turntable going round and round like this, and we have this little post on there, and you can see the shadow of that post. As this goes around in circular motion, and the pendulum goes back and forth in simple harmonic motion, we can see the shadow always stays right on that pendulum. So when the pendulum is right here at 0, that's equilibrium, and it can go out here to a maximum and out there to a maximum. But the radius of our circle is the amplitude of this thing, particularly when the angle is 0 here. But it's just the hypotenuse times the cosine of this angle would give us the position or where that pendulum is along here. And if we look at a pendulum moving back and forth with sand being deposited on a conveyor belt, it's going back and forth in a position here, and this would be time. So if we graphed that, we would get something very similar to that. Same thing here. This is a sonic ranger, and it's just bouncing up and down. This is graphing its position as a function of time, and you see we do get a nice cosine curve there. All right, so we found position as a function of time. Let's now do it with velocity. So as this ball goes around, that ball has some tangential velocity. And at that moment, it had tangential velocity in this direction. And at that moment, this cart has some velocity in that direction. Here is a triangle, there is a triangle. This angle will be the same as that angle. And the ball's velocity in that direction has a component in that direction. The component of that ball moving in circular motion is going to be the velocity of the cart in simple harmonic motion. And I did have to throw in a negative there to keep track of the fact that it's moving to the left. So tangential velocity is radius times angular velocity, and this velocity is going to be the hypotenuse times the sine of the angle to give us this opposite side. And then the radius of this is the same thing as our amplitude. So the radius is the same thing as our amplitude. Remember that the angular velocity is 2 pi f, so we're plugging in 2 pi f for the angular velocity. I'm going to move that a over to this side and substitute in for tangential velocity. I'm going to put tangential velocity, I'm going to put the 2 pi fa there, and I'm going to substitute in for the angle 2 pi ft, which we've already shown. So we now have velocity as a function of time. We can predict what the velocity of this cart is because it's just the horizontal component of this thing moving in circular motion. So there we have that. We'll do it one more time, but now we're going to do it with acceleration. That when that object is moving in a circle, it is accelerating toward the center of the circle. We say it has centripetal acceleration. Okay, so we have a triangle there, a triangle there. That the centripetal acceleration of the object moving in circular motion has a component in that direction, which will be the same acceleration of the cart here. We did throw in a negative because it was to the left. Centripetal acceleration was v squared over r. That was from circular motion. V is the same thing as r omega, so we're going to take r omega, but it gets squared. We'll end up with an r squared and omega squared over r, so we just are simplified and get r omega squared. Remember that omega is 2 pi f. And the other thing is we're remembering that the radius is the same thing as the amplitude. So 2 pi f is our angular velocity, but it gets squared. Everything in there gets squared. So we get 2 squared, pi squared, frequency squared, and then we're still left with the amplitude. All right, deep breath. The results of this are more important than the actual steps. The results just, these steps give us confidence in our results. but this acceleration we can find by taking the hypotenuse times the cosine of this angle, the hypotenuse times the cosine of the angle, and then I substituted in this for a sub c, and I substituted in this for the angle. And we have just found acceleration of our cart as a function of time. So we're going to put that there. One more piece I'm going to do. Remember that this right here, a cosine of 2 pi ft, is our position. So I'm substituting all of that in for our position. We're going to do a lot more with this in our next video. So just to recap, the period, time it takes to go all the way around, is the reciprocal of frequency. And also we can calculate the time it takes to go all the way around by taking the number of angles all the way around divided by how fast it's going around, its angular velocity. We can calculate its acceleration as a function of its position by combining Hooke's law with Newton's second law. We can use conservation of energy to calculate its position, or calculate its velocity as a function of its position by taking the fact that the spring potential at any point plus the kinetic energy of our mass at that same point is going to be the total energy of our system, which is going to be the total energy of the spring when it's fully stretched to its maximum. And we can use the fact that when something is moving in circular motion, the horizontal component of that will be our position, velocity, and acceleration of our object that's moving in simple harmonic motion. So we can find position as a function of time, velocity as a function of time, and acceleration as a function of time. That's simple harmonic motion.